All right, we're going to take our first look at polar equation graphs today, starting with Rose graphs. We'll probably have to do more than one video to get all this onto our notes. And speaking of notes, we've got kind of a couple of different things going on. You have a blank note sheet, 6.5 notes, looks like this on the left-hand side there. Then you have a sheet with some blank polar graphs. And I've got that kind of going on in the middle here. We're going to put some examples on there. And then you also have a yellow, or if you weren't in class, maybe get one from online, formula sheet that has these two tables on it. So we're going to start with the Rose curve graphs today, and we're going to start actually on the notes that you have. We're going to start with just a look at what these functions look like, and then do some tests for symmetry here, just to start off with a little bit of algebra before we dive into the graphing. So a Rose graph is called such because it has petals on it. So this is an example of what a Rose graph may look like. Okay, right here. So what I want you to notice is that this graph looks like it is symmetric over the y-axis. The equation for that graph is right there. R equals 4 times the sine of theta. And what we're going to do is we're going to prove algebraically that this is symmetric over the y-axis using one of the three tests that you see right here. Since we're looking at the y-axis, we're looking at number 2. And much like when we put in negative x into f of x to test for whether a function was even or odd, we are going to be replacing r and theta in our polar equations with negative r and negative theta respectively. So that is what we're going to try first. You might notice here we have two different things. We're going to try these first because, well, they're easier to put in. If those don't work, if we're testing for either symmetry about the x-axis, y-axis, or origin, we have these three different tests. We'll try these first. If they don't work, then we will move to this second set here. Okay, now there's no reason for us to test for symmetry over the x-axis or the origin because we can see the graph right there. We can tell that it looks like it's symmetric over the y-axis, if anything. So we're going to replace r theta with negative r, negative theta. And then if that doesn't work, then we'll try that guy there. Okay, so I have that right here, that since we're testing for symmetry about the y-axis, then we are going to replace r with negative r and theta with negative theta. And I've kind of done that already here in our equation. And then what we're going to do is simplify. If, when we get done simplifying, we end up with the same equation again, okay, and that's what all these tests show, and actually I should probably highlight that here. What we're trying to do is see if we can produce an equivalent polar equation. Okay, if either of those replacements down there give a equivalent polar equation. So in other words, we want to end where we started. So as we simplify here, I'm going to bring that negative r down. We have 4 times the sine, and really I probably should have brackets around this because those are both within that sine function. I can multiply those together. I have negative 3 theta, the sine of negative 3 theta. And if you remember from our identities, the sine of a negative angle is equal to the opposite of the sine of the positive angle. So I can rewrite this as negative 4 sine of 3 theta. And then we'll divide both sides by negative 1, or multiply both sides by negative 1. And we end up with the equation that we started with. So that means that there's symmetry in the y-axis. Okay, so now let's break this this graph down a little bit more and talk about these Rose graphs. So I'm just going to show you this on Desmos. I think it'd be the easiest way to do this. I have the same graph here. R equals 4. Actually, I don't. Now I do. R equals 4 times the sine of theta. So it has 3 petals, and that 3 is related to the number 3 in our equation. But what I want to focus on first is that first letter, the 4. Okay, so don't think I'm going to be able to write on this at all here. No, I'm not. So just you're going to have to identify what the equation is here on your own. That we have r equals a sine of theta. A is 4. or b theta, and b is 3. So it's r equals 4 sine of 3 theta. The first number I want to focus on is that 4 right there. The fact that the 4, when changes the length of those petals there. Okay, whatever I make that value, the length of those petals goes down to that same value. So right now we can tell this petal here, we'll use this one, the length of that petal is 2 units. Yeah, it's going down to negative 2, but the length is 2. Now it's 3. Now it's 4. Okay, so the A value tells us the length of each of those petals. The B value is related to the number of petals. So right now B is 3. And if I move B to 4, you'd expect it to be 4 petals, but you'd be wrong because there's actually 8. So that's kind of strange. Let's move it one more time to 5 and see that we're down to 5. And if we go to 6, we're now at 12. So anytime we hit an even value for B, it doubled that value to give us a number of petals. But the odd values had the same number of petals. Okay, so that's something to keep in mind. If I go to 7, it'll be 7. If I go to 8, it's going to be at 16, so on and so forth. All right, let's go back to our original. We said that this one was, actually, this is our original. We said that this one was symmetric in the y-axis, correct? Now, if I go to my even number of petals, this is actually symmetric in both the y-axis, or it's symmetric in the origin. Okay, so it's symmetric in both the y-axis, or it is symmetric in the origin. When I stay with my odd petals, they just are symmetric in the y-axis, but that is because the function we're dealing with is the sine function. If we were to switch over to the cosine function, now notice that our odd numbered petals, okay, I'm at 7 right now, this is now symmetric in the x-axis. Okay, I can fold this over the x-axis on top of itself, and if I go to my even petals, it's again symmetric in the origin. So no matter if you're sine or cosine, if it's an even number of petals, you're symmetric over both the y and x axis, or you are symmetric in the origin. If you are an odd number of petals, if you have an odd number of petals, then it depends if you have sine or cosine. Cosine, let me go to an odd number here. Cosine is symmetric in the x, sine is symmetric in the y. Okay, so we'll use that to help us as we go along here. What I'd like you to do now is we're going to go to our graph here. We're going to kind of bounce back and forth between our examples and our formula sheet here. So the first example on the formula sheet, and if you were in class today, remember we did this one in the second space. We left the first space open just in case we use that for some general stuff later on. If you weren't in class today, I don't know if you want to draw this polar thing by hand. I can try putting the blank ones up on Classroom. You can print some off if you need to, or just you could search for some free polar graphs online. So here is the first equation we're going to focus on. It's the one that we just dealt with. Okay, we're going to graph this by hand. What I want you to notice first is we have a sine function, and we have an odd n value, okay, which obviously we've kind of talked about this one already, but what that means is that we are going to be symmetric in the y-axis. If there were an even n value, it would be symmetric in the origin. Okay, or if there were a cosine, then it would be, and still odd, so the 3, then it would be symmetric in the x-axis. The petal length is going to be the 4 that we have right here. Okay, that 4 tells us that the petal length is 4, because A is 4. N is going to be 3, because, or N is 3, and since it's odd, we know that there are 3 petals. Okay, even you double that number. Now the period. The period is found the same way that we would find the period in a sine function that we were graphing on the rectangular coordinate plane. It's 2 pi over b, but in this case, obviously, we're not calling this b, we're calling it n. So we're going to say that this is 2 pi over 3. Okay, and that's something that we're going to put on our formula sheet as well. We're going to skip this stuff for right now. Okay. And obviously you don't have this stuff written on the formula sheet, so at some point you're going to want to pause the video and make sure you jot that stuff down. But in order to graph this right now, instead of dealing with this first petal and what we had to get to the next petal, what we're going to do on this first graph, for sure, this first graph, maybe even another graph, is make a what I call a reference graph. This is our reference graph right here. Try to fit this in near your polar graph, okay? And what we're going to do is we're just going to sketch the graph y equals 4 times the sine of 3x, or 3 theta. So we're going to treat that like an xy axis, and we're going to graph our period like we did. So we haven't done this in a while. Move this out of the way here. If I can I not do that? There we go. Okay, we're going to go out to our period. Not worried about scale at all right now, which is 2 pi over 3. And then we're going to split that up. That'd be pi over 3, pi over 6. And this is going to be pi over 2. We know that this is a sine function that has an amplitude of 4. Okay, so since it's a sine function, it's going to start at the origin. It's going to end then at the origin when it finishes its period. Not the origin, excuse me, at that midline. And then halfway through, it's going to go through that midline. It's a positive sine function, so it's going to start by going up and hitting its maximum. And it hits that maximum, I'd like you to notice, at pi over 6. That value is always 1/4 of the period. Okay? In this case, it's pi over 6. And then we're going to hit our minimum right here. So we're just going to do a quick sketch of this, and then what I'd like you to do now is continue this until we get to pi. Okay, so I've got this is 4 pi over 6, this will be 5 pi over 6, this is going to be pi, and this doesn't seem like, we've never done this before when we graph these. It might not seem like something that we need to do, but we're going to need to do it, and you'll see why in a second. And what I'd like you to do is label each of these points just like this so that we can compare them to the points that we get on our polar graph. So here we go. We're going to graph our polar graph here, and kind of talk about what it means to be graphing a polar graph. What we're doing here as we graph a polar graph is graphing values of theta between either 0 and pi or 0 and 2 pi. We only need to go 0 to pi because we have an odd value for n. When n is even, we're going to have to go all the way to 2 pi. Okay, and there's a lot of, I'm sure you have a lot of questions as I'm going through this. We certainly did in class today, but I think once we finish an example or two, some of this will kind of clear itself up. Okay, we'll probably have questions remaining, but some of these things will clear itself up. Okay, so when we let theta be 0, okay, think about what this becomes if we have theta be 0. 3 times 0 is 0. The sine of 0 is 1. So what we end up getting then, the sine of 0 is 0. So what we end up getting then is 4 times 0, which is 0. So that is representative of that first point A that we have on our graph right there. As theta gets bigger, as it starts opening up and we go towards pi, it is going to take on the same exact values that we have on this graph down below here. Okay, so but these are values of r on the polar coordinate plane. So when we have positive values like we do right there, we're going to be on the same side as our terminal side. But when we have negative values, we'll be on the opposite side, okay, or pi more. So when we are at a value of 0, or when theta is 0, we know that r is 0, okay? But our next point, B, is going to be when theta is pi over 6. Well, pi over 6 I already have marked down there, and our r value, see, this is now our r axis, this is our theta axis. Our r value at B is going to be 4. So that's going to be right here. Where's pi over 6? 1, 2, 3, 4 is right there. We're just going to label these 2, 4, and then this is 6 up here. So I'm just treating those red circles as if they are a radius of 1. Okay, so that's our point B right here. Oh, and I forgot to label my point A right there. And here's point B. Okay, so those values are getting bigger as theta gets bigger. So picture this theta opening up, and there's really no way for me to show that. I guess I could try with this here. So what we're doing is like we're picturing the terminal side. Oh, well, is this going? Oh, it is going to work. We're picturing the terminal side of this angle as we open it up. At pi over 6, we had a value of 4. Okay, but as we opened up, those values got bigger and bigger to go from that point A to the point B. If we were to trace those values, what it would end up giving us is this graph right there. So we're not going to plot anything in there. We just know that it makes that curve right there. And then as this continues to open up, when we get to pi over 3, down here you see once we get to pi over 3, we're at 0 again. So as it went to pi over 3, these values got smaller and it went back down to the pole. So I first started going in this direction, and then I came back in that direction. So even though we're labeling it A and B, I think those arrows help out as well. And here's where things get interesting. Between C, okay, I'm at C now. That A is also C. Between C and D, we have negative R values. So as this opens up from pi over 3 to the pi over 2, all the values are negative. Well, when you're negative, you're on the other side of that angle, or on that terminal angle plus pi. Well, when you're negative, we have a negative R value. Remember, it's plotting it on the other side. So when we get to pi over 2, excuse me, down here you see we're at our furthest value away that's negative, which is negative 4. So when we get to pi, that angle is pretty messed up, sorry about that, we're going to be down at negative 4, which is right here. This is actually the point for the angle pi over 2. So this is point D, and that's at negative 4. That's negative 4, negative 2, and here's negative 6, right? Okay, 4 for pi, that is. All right, so, or pi over 2, sorry. All right, so that means that we are going to go from that point C down to point D, just like that. Okay, and then I'm gonna stop at this angle. As that angle continues to open up, now we're gonna go from pi over 2 to 2 pi over 3, and 2 pi over 3 is right here. So once it gets to that angle, it's gonna be back at 0. But all those values are negative, so it's on the back side, and it's gonna be opening up like this. Okay, now if we would have stopped right there, notice that when we get to 2 pi over 3, I got to put my next letter, which is E right there. That's where I'm at right now on this graph. If I were to stop there, because that's the period, we'd only have 2 of our petals. Okay, and now's a good time to kind of notice that, hey, look at these bumps in the graph. There's 2 of them there. We only have 2 petals. This third bump in the graph is going to give us that third petal, and that's not a coincidence. Those bumps in the graph basically give us the petals on the polar graph. So we need to get that third thing, and that's why we had the third bump, and that's why we had to go all the way to pi. We had to extend to pi, and that has to do with what we set up here. We have to graph from 0 to pi to get a full graph. Okay. If we were to, well, let me finish this first. So our point at 5 pi over 6 is 4, so I'm right there. So from that point E, I know that that's where we're headed, and that's F. And then as we come back down towards the pole, that'll complete our graph. So there's our first rose graph. Okay, that was the one that we tested the symmetry on, and we completed it by graphing from 0 to pi and relating it to this reference graph here. Now what I'd like you to notice is that the first petal tip, that's really the first petal tip is what I'm talking about there, was right there. Okay, that point is always going to be at whatever I'm giving it as a polar point, r comma theta. That point, if it is sine, the first petal tip is always going to be at A as your r value, farthest one away, comma, and then your angle is going to be pi over 2n. That's 1/4 the period. Okay, That's 1/4 the period. That's where that comes from. So in our case, pi over 2n, well, a was 4. Pi over 2n is pi over 6. That was our first pedal tip right there. 4 comma pi over 6. Because I'm not always going to have you guys make this reference graph. This takes a while. Actually, I don't think it's a bad idea, because once you get good at it, you can go pretty quick from that to the polar graph. But we're going to do a little shortcut here. We get our first pedal tip like this, and then know that from one tip to the next tip is just going to be adding 2 pi over n, which is the period. So 2 pi over n was 2 pi over 3. We're just going to add the period. So from here to here, you could just add 2 pi over 3, because that's the period. But the only reason that works is because we have an odd n value. When it's even, we're going to have to do half of that, which is why we end up with double the number of pedals. All right, so we add 2 pi over 3. Remember, this was pi over 6. Pi over 6 plus 2 pi over 3 would be the same as 4 pi over 6. Hey, look, we get 5 pi over 6, and that's where our next pedal tip ended up being, 5 pi over 6. So instead of making a reference graph, basically what we could have done here and said, okay, do this a little bit quicker. My first pedal is at pi over 6. If I add the period, which is 2 pi over 3, my next pedal is going to be at 5 pi over 6. And they're both going to be 4 away, and I'll be doing this on a polar graph, so it'll be easy to get. If I add 2 pi over 3 to that, my next point is going to be at 3 pi over 2. Well, there are my 3 pedal tips, and then we'll just do a sketch in like this, and it'll be much faster than making that reference graph. Okay, let's try another example here, and we're going to do one more where we use this reference graph. Actually, no, let's not. Let's just go right to using that idea that we had here, because we've got another odd n value. Our pedal length this time is going to be 3 because of that 3 value. Let's just write a equals 3. N is going to be 3, or n is 3, which is odd, which tells us that we have 3 pedals again. The period is going to again be 2 pi over 3, but here's where things change. Because it's cosine, okay, now if you picture that reference graph that we just talked about, if you were dealing with cosine, cosine starts at the maximum and then comes down. It's going to start at 3, okay? It's going to have all the same, let me just really quick do a reference graph here, I just can't help it. Okay, it's going to have the same values here, 2 pi over 3 because it's the same period, pi over 3, pi over 6, 5 pi over 6, okay? And we know that this thing is going to start at that maximum, come back down through, hit the minimum, go through the midline, end up there. That's what this guy is going to look like, okay? And then we will have to extend this again, 2 more, like we did before, and end up right there, okay? Actually, that's not what it's going to do. It is going to end up right, it is, isn't it? Okay, so we'll extend that in a second there. So let's start plotting this. Let's talk about this first pedal thing here. Since it is a cosine graph, cosine will always start at the maximum value A, just like the normal cosine graph that we've done. So, that'd be a 3 in this problem. 3. But it's going to have an angle value of 0. So in other words, the cosine graph is going to start right here. 3 comma 0. So here's 2, 4, and 6. So at 3, 0 is where we're going to start here. That's going to be our first pedal. The period is 2 pi over 3. So that's what I want to add to get to the next pedals. So if I add 2 pi over 3 to that, I'm going to get 2 pi over 3. So I'm just going to put down where 2 pi over 3 is right here. That's going to be where my next pedal is. If I add 2 pi over 3 to that, I get 4 pi over 3, which is right here. Okay, so I know that I'm going to have a pedal tip here, and I'm going to have a pedal tip here. I'm trying to find 3. There we go. So this is what this is going to end up looking like here. I'm going to start it where it does start, which is from right there. And if we were marking our points again, that'd be A and A. Okay, and then this would be the B where it's crossing through. Okay, I'm not going to go any further than that, but then it would come down through here, come back up through at 2 pi over 3. Actually, this is right there. Actually, if I stopped right there, sorry, I wanted to stop right there because that's where I'm at, 2 pi over 3. If I stopped right there, that is what I get from one period. I have to continue to pi in order to get the full cycle. Okay, so that would give me this and then this. So we started at A, went back in towards the pole, came back down through, so there's B and then C if you want to keep marking them. And then we went back through, came back up this way, back down, and we ended at A. A was our start and our finish. Okay, so there is a cosine graph with an odd number of petals. All right, I think it's a good time to take a break. And in our next video, what we'll do is we'll fill out the formula sheet, take some of the stuff that we just talked about, put it on a formula sheet, and we'll finish with a few more examples.